The force spring constant is given by the force divided by the displacement. So we have 6 newtons cause a displacement of 0.03 meters, and that gives us a force constant of 200 newtons per meter, which, if you do some changes with the newtons, it comes out to about 200 kilograms per second squared. So these units are interchangeable. For part B, we're asked for the angular frequency. The angular frequency, omega, is the square root of k over m, which is the square root of 200 newtons per meter over 0.50 kilograms. And this gives us 20 radians per second. The frequency is the angular frequency divided by 2 pi. So this gives us 20 radians per second over 2 pi radians, which gives us 3.2 per second, or 3.2 hertz. And finally, the period, not finally, for B, the period is 1 over f, which is 1 over 3.2 per second, which is 0.31 seconds. So assuming we now, instead of pulling at 0.02 meters to the right, we say we give it another initial displacement and initial velocity, and we want to find some equations. So just for part C, we're going to assume that the amplitude given earlier is no longer valid. So we can say that the amplitude, if we know initial displacement and initial speed, is going to be by the initial displacement squared plus the initial speed in that direction squared divided by omega squared. So this gives us 0.015 meters quantity squared plus 0.4 meter per second quantity squared divided by 20 radians per second quantity squared, and this gives us an amplitude for part C of 0.025 meters. It also can get us the phase angle for this oscillations, which is tangent inverse of minus initial velocity over omega initial displacement. So this is tangent inverse of minus 0.40 meters per second over 20 radians per second times 0.015 meters, and that gives us an angle of about minus 35 degrees, but remember we have to be in radians, so change this to radians by taking the 53 degrees times pi over 180 will give you that number. So now for part C, which is asking for the function of x, the displacement as a function of time, we have a new amplitude of 0.025 meters times the cosine of omega t. So this is 20 radians per second times t minus plus the phase shift angle, so plus a negative 0.93 radians. Once we have the displacement, the velocity in the x direction then is going to be the derivative of this. So we're going to get a minus sign of all of this, and then we're going to pick a 20 radians per second times 0.025, and that will give us a negative 0.50 meters per second sine of everything we had before. So radians, 20 radians per second times t minus 0.93 radians. And if we take the derivative one more time with respect to time, we get negative 10 meters per second squared cosine, again 20 radians per second t minus 0.93 radians. For part D, we can use the formula that says that the velocity as a function of a displacement is given by omega times the square root of the amplitude squared minus x squared, where the velocity at some point x, that's going to be this x here. Now we have a choice to make. Since we're given an initial amplitude of 0.02 in the statement of the problem, I'm going to use that as my amplitude and not the special case that we got in C. So in case you see me using 0.02 instead of 0.025, know that I went back to the original problem for parts D, E, F, and G, so that you know where those numbers came from. And notice that if I want the maximum of this value, that means that x has to be 0, right? So if I'm looking for the maximum value of the velocity, that's going to be omega a actually, right? Because if x is 0, I get omega times square root of a squared, which is a. And if I do this, I get 20 radians per second times an amplitude of 0.02. Again, I'm using 0.02 because the original problem started with that, and that gives me a 0.40 meters per second. So keep in mind that if we translate this plus or minus, then the maximum would be the positive, the minimum would be the negative, right? So that's and velocity is directional, so the plus and minus are going to be different. Now for part E, we're given the acceleration. Acceleration, again, if we think of this, is going to be a sub x is going to be minus omega squared x, and now we can say that a max is going to be at the amplitude, which would be minus omega squared a, and the minimum be opposite, right? And the minimum would be at minus omega squared a. So it depends on which oscillation we have that dictates the maximum and the minimum. Notice that the magnitude of those would be exactly the same. So the maximum would be at a positive 20 radians per second quantity squared times an amplitude. Again, I'm going to use the original one given. So this will give us 8 meters per second squared. And that means that this is going to be negative 8 meters per second squared. For part F, we're told find the velocity when the amplitude is halfway. So we know that v sub x equals from its halfway from its initial position to the equilibrium position is given by omega square root of a squared minus x squared, and here it means that x equals a over 2. So we can use, remember that the velocity function is given by that equation, so we have minus 20 radians per second square root of, this is going to be 0.02 meters quantity squared minus 0.01 meters quantity squared, and that gives us a speed or a velocity of 0.35 meters per second. Negative meaning it's heading from its stretch to the equilibrium. Yeah, so because it's going to go back that way. We want the acceleration at that point, so we can say a sub x is omega squared, negative omega squared, times the amplitude at that value x. So that's going to be, or it should be just x, not amplitude at x, just the value of at x. So this will give us minus 20 radians per second quantity squared times 0.01 meter, that's the amplitude. So we will get minus 4 meters per second squared. And part G is asking for the energy. So the energy complete is given by 1/2 k times the amplitude squared. So this is 1/2 times 200 Newton per meter times 0.02 meters quantity squared, or 0.040 joules. The potential energy does depend on the value, and that's given by the value at that position squared, so it's 1/2 kx squared instead of a squared. The total energy is independent of position because it's the sum of potential and kinetic energy. So this is 1/2 200 newtons per meter times 0.01 meter squared, or 0.01 joule. And then the kinetic energy, you could do it one of two ways. Since you know what the total energy is, you can say kinetic energy is E minus U, which will give you 0.03 joules, or you can say it's 1/2 m Vx squared, and that's going to be 1/2. The mass is 0.5 kilograms, and we found the speed to be 0.35 meters per second quantity squared, and that gives you exactly the same value as before.